So, well, my intention here was that I was going to talk about um, a number of topics, and especially not now at this point. Um, I won't be monitoring chats, and also if you have any questions, I'm not going to be able to answer it really at this point while I'm going through everything because it's easy for me to get distracted. But my intention was here to talk a little bit about some physics, some astronomy, some oceanography, some chemistry, some meteorology, some geology, and overall science wonderment. And we'll see how far I can get when it comes to all of these topics. So what I was going to do was I was going to talk a little bit about the Earth geometry, Earth orbital geometries, and then the Moon orbital geometries. Um, Over here, what we have is this shows our Earth's orbit around the sun. And basically what we get here is this is what allows us to have our seasons. And I was going to talk a little bit more about this. However, due to lack of time, let me just go on to the next point, where in addition to the Earth orbiting around the sun, we also have our moon orbiting around the Earth. And it's because of this tilt of our axis that we actually get our seasons. And so that tilt of the axis is about 23.5 degrees. The Earth's axis with respect to the Earth's orbital plane around the sun. So we have these orbits because it's basically a nice balance between the laws of physics having to do with Newton's laws of motion and Newton's law of universal gravitation. Uh, when we talk about the geometry between the Earth, the Moon, and the Sun, this is where we get the phenomenon of tides. The tides are actually a type of wave. And what this diagram is showing is it's showing the configuration of when we have a neap tide and when we have a spring tide. Uh, Basically, a neap tide is when you have the configuration of the sun, the earth, and the moon at a 90-degree orientation. Spring tide is when you have them in alignment. And what you have here is a situation where, since it's the moon that is the most significant of the effects when it comes to tides because of the gravitational attraction between the Earth and the moon or the Earth and the sun. The spring tide, you have an additive effect between the sun and the moon. So the tidal bulge from the sun and the tidal bulge of the moon add, and you get the highest high tides. High tides would be on this side. And then on the other side would be the lowest low tides. On the neap tide, since you're competing between the moon's gravitational attraction and then the sun's gravitational attraction, you have the high tide still on the moon side. And so you don't have quite as high of a high tide and you don't quite have as low of a low tide when that occurs. If you're looking at this diagram, disregard, this is wrong, disregard the configuration of the continents here, because that is wrong. The Earth does not rotate with the continents configured like that. The Earth does not rotate around the Atlantic Ocean, and so this is on the right is a better depiction of what actually is of what actually should be the orientation. So to give you an idea in terms of actual tide heights or the tidal range, here's a time series, 1 month's worth. So what we have here are the high tide, here are the low tides along here. And notice that during the spring tides, you have the highest high tides, lowest low tides, new moon, full moon. And during the neap tides, what we have here, we have not so high tides and not quite so low tides. It's interesting that what you have is here's the new moon phase. This is the full moon phase. This is the first quarter, and this is the third quarter. Sometimes when you think of quarter moons, you kind of get the idea, oh, if it's a quarter, it must look like a crescent. In actuality, quarter moons, they look like half moons. And that's because you think of the quarters as the whole cycle of the moon's orbit around the Earth, and it takes roughly about a month, depending on your viewing perspective. It's either 29 plus days or 27 plus days, whether you're talking about a sidereal month or something called a synodic month. So the Bay of Fundy is interesting because down here in Annapolis, we have a tidal range maybe about a couple of feet or so. But if you go a little bit further north to Boston and Cape Cod, the tidal range is about 10 feet. If you go even further north to Canada, this is the Bay of Fundy. So you can see here's Long Island, here is Cape Cod, Maine is over here. Bay of Fundy was formed by geological processes of folding and also glacial scouring long ago. And the thing about the Bay of Fundy is that it has the highest tidal range anywhere in the world. And down here, you can kind of get an idea that if you go to the Bay of Fundy, you can actually see how much of a difference low tide and high tide end up looking like. One of the results of places like the Bay of Fundy where you have a major tidal ranges is something called a tidal bore. And this occurs in regions where you have high tidal ranges. And what forms is the something called the tidal bore or the tide wave. Not tidal wave, but it's an actual wave caused by the incoming tide, incoming high tide. And then so again, this is the Bay of Fundy. You can see this is actually the tidal bore coming up the river. And if you're a surfer, you can actually surf in some of these locations. The cool thing about this is that usually when you think about surfing, you're at the mercy of the weather conditions, usually hundreds, if not thousands of miles away, where you get a storm. The storm causes the formation of many swell waves, and then the swell waves hit certain regions like the North Shore of Hawaii, and you get that nice, those nice Hawaii 5-0 kind of waves. Maybe you know what I'm talking about when I say Hawaii 5-0 waves, and these surfing waves. The thing about the tidal bore is you're not at the mercy of weather. You're at the mercy of the motion between the Earth, Moon, and the Sun. We know very well what those are. So these tidal bores actually appear on schedule. It comes right on schedule. So if you're a surfer, you can actually schedule your surfing. This is the configuration of a lunar eclipse. Here's the configuration of a sun eclipse. The lunar eclipse is when you have the sun, earth, and the moon in alignment, and the moon goes across the shadow that is cast by the earth. And then so this lunar eclipse, you tend to, you don't actually see the moon disappear. It actually gets dimmer, and then usually during totality, it takes on kind of a sort of a reddish tint. The more dramatic sun eclipse or the solar eclipse is when you have the new moon. The new moon is the moon that you do not see, and that happens during the day. And what happens is the moon blocks the sun's rays from reaching certain parts of the Earth's surface. Given this diagram, you'd be tempted to think that these actually, the eclipses actually occur on a monthly basis. They do not, and just really quick, what I'm just trying to show you here is the reason that these eclipses are fairly rare is because the ecliptic plane, this is the plane defined by the Earth's orbit around the sun, and then the moon's orbital plane, that's the plane defined by the moon going around the Earth. They're off by about 5 degrees. And incidentally, this is the Earth's equatorial plane. This is that 23.5 degree tilt that we're fairly familiar with. So because of these offsets between the ecliptic and the moon's plane, you don't have the eclipses occurring on a regular monthly basis. As far as use of solar eclipse glasses, contrary to what you might think, you do not use solar eclipse glasses. You don't have to use them only during solar eclipses. You can use them any time of the day. Okay, it's you only use them when you get tempted for some strange reason to be staring up at the sky and up into the sun for long periods of time, and usually that occurs during a solar eclipse. And one of the things are these eclipse glasses are actually designed to protect your eyes. Do not try to do this, where you put like 9 pairs of sunglasses to look at the sun. That's, you're not supposed to do that. And also, that may actually be dangerous to your eyes. You may not be actually helping your eyes. There are actually 3 kinds of eclipses. You have the partial eclipse. This is what we would have seen through the eclipse glasses in 2017, which I'm going to talk about shortly. Over in our region, we would have seen a partial eclipse. A little bit further south, this is where you get the total eclipse. And there are certain times when, because the moon travels in an elliptical orbital path, like actually all celestial bodies actually orbit in somewhat elliptical paths. Sometimes the moon is a little bit further from the Earth, so that when an eclipse does occur, it doesn't quite cover the whole sun, so you get what's called an annular eclipse. And I just wanted to show this so that Professor Karp and Professor Sivalingam, they've been bugging me about making sure to include chemistry in this talk. And one of the things I was thinking, well, this is tides and eclipses. I'm not sure I know a connection, but this is an actual connection where sunlight will actually interact with certain cells in our eye, in our retina, and that causes a reaction with an enzyme forming vitamin A. And that vitamin A is actually important for the health of our eye and for good vision, specifically low light vision and color vision. This is the normal pathway during normal light situations. When you have too much light, like when you're somewhat tempted to stare at the sun for long periods of time, like during an eclipse, what you end up getting is you actually end up getting sort of a poisonous form of oxygen gas actually interacting with our retinal cells and causing cell death. So this is the reason why we need to have solar eclipse glasses. It's actually more of a photochemical situation, rather than what people used to think was that you don't want to stare at the sun because the sun's rays will burn your eyes, similar to how a magnifying glass can focus the light and burn something. That may be part of it, but it looks like it's really more of a chemical process. Just to let you know, in 2017, this was the path of the total solar eclipse that went through our region. Notice that over Maryland, it was about an 80% totality. A little bit further south was a 100% totality. So what I did actually, and some of you may have also taken advantage of this, is when this occurred, and this was the week just prior to semester start, traveled a little bit further south. I actually traveled down to South Carolina, to Greenville, and actually experienced totality. And so I had a really, really nice experience actually interacting with some kids from Danville, Virginia, who a couple of the kids were not even interested in going with their parents to experience this. But when they did experience totality, they were totally moved by the experience. This is a picture that I took. You've seen thousands of pictures probably when it comes to these solar eclipse. But for me, this was my own personal picture, and it was straight, just a straight camera, unfiltered. I took a snapshot, and there it is. So that's my picture. Um, I also remembered I should actually try to take a picture of what it looked like outside. This is what it looked like outside. This is in the middle of the afternoon, and it got darker than night. Ended up happening was I was a little bit dismayed initially because all of the automatic lights went on. And I was thinking, oh, I wish that didn't happen. But in retrospect, I'm glad at least some of the lights went on. Otherwise, if I tried to take a picture, I would have not have anything to show you. It would just been a dark screen. I wanted to show you. I actually grabbed these series of satellite images. I grabbed these real time, and as you can see, it's as preliminary, non-operational. So these were happening, and I was grabbing these as the shadow of the moon was actually transversing the United States. And this is actually what it looked like from outer space. And so I was quite happy. I wasn't sure what to expect, but I was all jazzed up when I actually grabbed these images and I saw that you can actually see the eclipse shadow traveling across. Just real quick, this is a kind of a unique picture by somebody who was able to snap a picture while on a Southwest Airlines flight. And during that Southwest Airlines flight, he was able to speak to the pilot. He had already researched the fact that the flight was going to be passing close to totality, and he was able to get a window seat and talk the pilot into deviating just a little bit enough so he could get the perfect picture. Anyway, there's a cool story about his being able to get on the flight and then be able to snap this really unique picture. So those pictures I took of my personal eclipse experiences. This is a really cool picture. I think the coolest picture I have is this. This is actually Professor Barber's family. Here's Professor Barber, physics professor and the physical sciences department chair. Here's his family. And what I wanted to show was that he also traveled a little bit further south to a different location and wanted to experience totality. Keep in mind that they've been staring at the sky for about an hour routinely. This is a few seconds just before totality. Even after staring at the sky for that long, at this moment, I think this is the coolest thing to show. This is the wonderment of science. And everybody from the youngest to the not so young people, I think they were all amazed by what happened here. And I think it was something that those who did experience totality will always remember. One of the reasons I bring this up was during that August 2017 eclipse. The cool thing about that was the eclipse did happen throughout the United States. However, not all of the United States experienced totality. And I know I had a student who, when I related this story, they talked about how it was the most hyped up thing in August of 2017, and he was not impressed. And I could understand that. It really was hyped up. I think you get very impressed if you actually experience totality. And so the reason I emphasize that is that in exactly 3 years and 2 days, on April 8th of 2024, you will have the opportunity to experience totality again. And you just have to travel not too far, but keep that in mind. I highly recommend if you have the, if you're able to, travel to where the path of totality is and do experience where you actually see 100% of a total eclipse. Anyway, that is very much an abridged version of what I wanted to give, but I'm not sure we have time for questions. perhaps I could entertain those at a future session of mine. And so anyway, April 8th, 2024. It's in about 3 years. Thank you for listening to me. I hope at least part of it was new information. Hopefully, part of it was somewhat interesting. Somewhat interesting.
Yeah, Dan, that was fantastic. That was really good. The abridged version really, I think, hit all the highlights, and we had lots of interdisciplinary discussion. I'm glad you included the chemists because I knew they were kind of a little, they were on me for making sure we needed something there. But I think the firsthand accounts of the 2017 eclipse that you were able to see, and you were able to show some great pictures there. And then, of course, the mention of what's coming in 3 years. So the chat basically was lots of excitement about what you were talking about, as well as the excitement of the 2024 eclipse to come. There's a good chance that a lot of people from this club will be planning a trip in 3 years. If everyone's together like this in 3 years, and that's just heartwarming, I think. So that's very cool. And that's my baby upstairs. That's what you may be hearing now. I'm going to go ahead and stop the recording.